quick and dirty Python conclusions. So I want to talk about the conclusions, and I want to talk about the small project I made, a Raspberry Pi and Analog Discovery Playground. It's in Python, and I actually had a lot of fun doing it, and that's because there was less Python than fun in the project, but I will talk about it later. But first, the conclusions. So I still hate Python, I still don't like it. But now that I understand it a bit more, I see its place in the world. I see that it's important. Maybe I see that it's important, but I still don't understand why it is used so much, why it is used in areas that it shouldn't be used. But maybe that's because of business and money. But maybe this is for another time. So these are my conclusions, and then this is my project, the Raspberry Pi and Analog Discovery Playground. So if you have these devices, you can do it. It's Windows only, unfortunately, but I also made a simulation branch, which is Linux only, that uses, well, just simulates the serial communication using socket and a serial, like two intertwined, you could say, serial ports. Yeah, so there are the requirements. There is the sim and the live branches. You can read all here. The only thing I will say, I prepared 3 examples. UPager, which is like a UART pager application. It simulates, or it utilizes asynchronous UART communication for transmitting text. Then there is UWeather, which has the BMP sensor connected in the live branch, and it basically reports temperature and pressure over like 10 seconds and then sends it to the analog discovery, and then you can do whatever with it on your computer. And then there is UTAG, so would be the RFID sensor, and I just made it possible to read and write RFID tags. So now with this, we can go to the code. And this is the code. So this is for the UART pager. On the left will be the code from Raspberry Pi, and on the right from the analog discovery, or like, let's say, the computer connected to analog discovery. What's important, that I will be showing code from the live branch, but here I will have a demonstration running on the sim branch because it is just easier to show. So first, let's maybe prepare the demonstration, and well, it's very easy. So the first thing you run is pts start on the sim branch, and it returns you 6 and 7. So these are the devices you have to do. And if you go to edit, okay, so probably some issue. I will ignore it. So 6 and 7. The issue is that my editor is broken. So if I do inspect, I get an error, which is not nice. Okay, so after this, if you install all the dependencies, then you can just activate the virtual environment. Same here. And I will clear to just be nicer. And yeah, so let's first do the demonstration. So yeah, this is the analog discovery. It's in the UI. I don't know, I made a GUI using tkinter. I will talk a bit more about it. And it's quite hard to show, but if I send something like hello, then we get last received hello. We can send world. I made a typo, so I will fix it. World. And if I send it, it overwrites here. I will also show how I did that. So it's a simple pager. You have received and sent text boxes, and then the received is immutable because you cannot change what you receive, of course. and then sending, and here I can like write anything and it will be here. Oh, that's the simplest of this all. And now I want to show the code. So first I utilize well, I set timeout to 0. Why? Because when the serial library is actually blocking, but the UART for the analog discovery is non-blocking. So if it does not have any bytes in the buffer, it will not wait for them. So I just made it both ways to be non-blocking, and then I made some cool loops. So what happens here, I start the serial port on TTYS0, which is mapped to the UART on the Raspberry Pi. And then I define a function. This function has a receive buffer, so I implement it in software, not in hardware. And then while true, I start reading bytes. And then as soon as I read a non-null byte, then I know that I started receiving a message. And so if I start receiving a message, I start appending it to a buffer. And then this one takes the last element of the buffer and checks if it's the signal end. So signal end in both programs is hex 03. You can look at the ASCII table what that byte means. And then if I receive this, then I take the buffer. The message will be decoded without the last byte, which is the stop byte. And then I clear the buffer because I've read the message. And then I write it to the last received place here. And what this is, these are ANSI escape codes. And just Google what ANSI escape codes are, but this basically allows that I can have this updating in this line. I could also make it so that I would have it only in 2 lines, the entire program, and it wouldn't change. But then I would have to use also ANSI escape codes for the input, and I would have to make some input changes. And then after receiving a message, I go to sleep for a quarter of a second, just because, yes, it's not a lot. I don't know why I did this, I don't remember now, but yeah, so that maybe you don't receive messages constantly. So this is the function for receiving, and then what I do, I start a new thread with this function, which is a daemon, so it runs in the background constantly. And so I start it here, and what it does, it just on an async thread just waits for messages, and if it has messages, then it writes it to the console. And well, Python takes care of like multi-threading memory stuff, so I don't need to. And then when the thread is started, then I do this. This try except is so that if I press Ctrl C to leave, because I did not add a leave command, then I won't get error dump. It will be the message leaving. And then sending is actually very simple, because I just input and then write it to the serial port, and then after writing the message, I write the stop byte. So this is on the Raspberry Pi, and this is now on the analog discovery. So this is very similar. It is just the code is a lot more cluttered because because I added a GUI. So first I also set the signal end byte. Then UART transfer and UART receive pins on the analog discovery are 0 and 8 in my setup. And then I make a class window. So this class takes some, like, this is written by ChatGPT. I just modified it to add this message queue. So when here I write it immediately to std out, because it is a GUI, I need to update the GUI. So I add a message queue which takes strings, and on the separate thread would be putting messages that it received to the queue. And here we have the GUI. and then here I initialize the UART, but before that I want to talk about that I start the thread with this in the same way as before, and this is the same code, but instead of putting the message to std out, I put it to the queue. And what happens, I then run a function every so often that tries to extract messages from the queue until it's empty. And then after another quarter of a second, it checks the queue again. So this is what runs also in the background, you could say, to check for the queue and update the GUI with the queue. So there I have set rx text. Here it's just GUI stuff. But before I start the thread, I also set up the UART. So this is UART setup from the PyWF library. So everything is documented there. And then I receive 0, so I initialize the UART, and then I store it in the class. And then the thread starts, just as I've said, and we start checking for the messages on the separate thread. And then I have in the main program, we initialize the analog discovery. That's very simple. Then we start basically the GUI application with the main loop, and that's it. It just works. All right, the next example is the uWeather. So this is weather reporting over UART. So this time I will start talking about the code, and then I will show the demonstration. Interestingly enough, now I think I will need to fix it. This print statement and this print statement worked on the sim branch, but do not work on the Raspberry Pi. I don't know why. Maybe like the Python version on I'm running 3.12, there was 3.11, so maybe a difference. But well, first I will skip over the make CSV function and we will come back to it. Then again, I start the serial port. Then I start the I2C bus for the BMP sensor, and I initialize the sensor. And then I define the signals used. So this works basically in the same way as previously. But instead now I'm just receiving on the Raspberry Pi, and after receiving I send. So it's now not asynchronous, it's synchronous communication using UART. So first I'm waiting for some signal. So if I get a signal enquiry, so this is the hex 05, then I start the measurement. So I write the acknowledge so that we start the measurement. Then I make measurements every 1 second. So this is 10 measurements. Nice by Python to put 11 here. But 10 measurements every second. So I get temperature, get pressure, and then append this to the lists. And then I make a CSV after the measurements are finished. So make CSV, it just makes a CSV file. I zip the iterators, enumerate over them so that I can put the first column will be time because the measurements are taken each second. And then I save it to takes latest, simple enough. And then after making it, I open the file, this time as binary I don't know why. I think it doesn't matter on Linux, although on specific file types it matters in Python. No, don't know what is the difference. I thought it is using the C call to fopen, but whatever. Then I just write the contents of the files since it's ASCII, so it will work. I think, yeah, the read binary makes it ASCII. Okay, whatever. So I write what I read from the file, and then after writing the contents, I send the signal end so that I stopped the measurement, and then I print information to the user that the measurement is finished. And then on the analog discovery side of the program, we again, bake CSV. This is reading. So I strip the signal end and then write the file again because I get the same bytes. So I just write them as a file. Then I define UART transmission and receiving pins, and then the same as was before. I just start initialize the UART, initialize the receive buffer, something which is not needed here because I'm only receiving bytes, not a lot of data. And then I send the signal enquiry to ask for the measurement, and then I wait for signal acknowledge, and then I start measuring. So I made a nice gen to spinner type sequence. I will show it in a moment. And then I'm waiting for data. And when the data comes, this is basically the same as before. This time, instead of printing the buffer to std out, I'm making a CSV out of the buffer. And this else here just is the spinner. So I again use ANSI escape codes to write the sequence. This actually is taken directly from Gentoo. I scoured my system for this piece of code, didn't find it, and I found it on the wiki, on the Gentoo forums. And then after I print that measurement is complete, and I close the connection to the analog discovery. So now the demonstration. So how it works, first you start the Raspberry Pi program, and this time Raspberry Pi works like a server, so or like a daemon, so it just runs in the background and you don't really need to touch it. And then if you want to take measurements, you just Python uweather ad and then measuring. So this is the Gentoo spinner here. And after 10 seconds, we get that the measurement is complete, and here it's done. And so we can take a look. If I go, I need to see what happens. I know what happened to my config. So this is the transmitted data. In the sim branch, these are just random numbers. So this is what I get. And you can verify that Rx is the same. We can even diff, and we get no output, meaning the files are exactly the same. And because this works like a server, we can also send a request for more measurements. And Raspberry Pi just waits for us to ask for measurements, and it performs them. So I think this is quite a nice feature. And then after that, it uploads the measurements again, and we can check if they are the same, and well, they are the same. And the last example shows an RFID tag, and it again has a GUI which clutters the code by a lot, but I don't know. I made it because I was really bored and I really liked the project, so why not give it a nice interface? So again, we defined some signals, so signal end so for this as the stop bit, we could say signal acknowledge as the acknowledge, and then we have read and write. These are commands, so that if we receive read, then we know that we are reading to a tag, and if we receive write, we know we will be writing to a tag. So again, in this example, the Raspberry Pi works like a server, so it just waits for the commands from the client, which is the analog discovery. So first we initialize the serial port, we initialize the reader using I2C. This time we're using a library which is even simpler. We do not even need to initialize I2C. It just initializes itself. And then while we start the server again with the keyboard interrupt, but here at the end we have gpio.cleanup and in the finally statement. So no matter what happens, if we crash, if we do Control C or anything happens, we will clean up so that we won't break the I2C in Raspberry Pi, at least break. We will not break it. It will be fixed after a restart. But yeah. Then we again do a while true to wait for bytes, and we read a single byte. And then we check if it's reading, then we do reading routine. If it's writing, we do the writing routine. So the reading is very simple. We place the tag on the sensor, and actually this read method is blocking. So the sensor, the program will actually wait for us to put the tag. I didn't know about it. That's why in the GUI, I think I will show it in the read tag. I first show the box, which is message box is blocking. So this was like a way to place the tag on the sensor so that you wouldn't be, let's say, you wouldn't be surprised as the user. But no, it is actually blocking. So I just added an additional print statement just for redundancy. And then I read the data. It returns a tuple, the tag ID and the contents. And I just write it straight to the serial port with the ID and the content separated by a semicolon and encode it so that it's in ASCII. And then I write signal end so that I wrote the tag and the data is sent, and then I wait to receive an acknowledge so that the client received my data. If not, then it will hang the program and you will just exit with it with Control C. Simple enough. I think you would know that if the read wasn't successful, you didn't get the data here, that something is wrong. Then we can also do here in the read tag, we send the signal read and we wait for the bytes to come. And we do the same thing with byte array, signal end, then signal acknowledge, we decode, so it's the same as in the last example, but then ID content, we split it at the semicolon just once, so the first semicolon, I do not expect a semicolon in the ID, there might be in the content, so I split once in the first one, which is this one, and then I show the information that the tag was read successfully, because it might still crash here. And then I just update the ID box with the ID, and then I put the contents into the text box. I will show the GUI later. Then writing the tag is pretty much the same, but in reverse. So in the analog discovery part, I put on the ID box the ID is constant. Then I get the content to write from the text box, and then I show info to place the tag. Again, here the write is also blocking, but yeah, I put it here so that for redundancy again. Then I transmit signal write, so the Raspberry Pi will select this path of the if statement. Then I send the contents, I encode it so that you get the string on the Raspberry Pi. Then I send the signal end so that this is the end of the content. And then I wait for the signal acknowledge. And so what happens here, if I receive signal write, then I wait for the data until signal end, I decode it, and then I write it to the tag, and I send back signal acknowledge that the write was successful. And here, after receiving the signal acknowledge, we have tag successfully written, and we finish the subroutine. We finish the function. And so this is exactly the same. Here again, we open the analog discovery. We start the start the GUI and start the main loop. And again, here we have the UART setup, and then we assign it to the internal UART. And well, that is all for the UTEC. So now a quick demonstration. So again, we get a GUI. This one is a bit more simple. Well, a bit more simple. This one from the sim branch is actually very crude. So if I press the read, I place the tag on the sensor, but there is no tag. So if I press OK, it now waits for the signal acknowledge from here. Normally it's non-blocking after the OK, but because I don't have the tag, I just input tag data. So let's say I write hello tag and read successful. And here if I go tag successfully read after pressing enter, if I press OK, then I get the tag ID. The tag ID is constant. I didn't show it here. I don't have the sim sim code, sim branch code. But I just have a function which asks you here on the terminal for the data to the tag, and the ID is assigned. I just pressed random numbers on the keyboard, and then tag data is successfully read. We can also write the tag hi mate, and we can send. We place a tag, so we assume it is, and then tag successfully written. Okay, place the tag on the sensor, then write it to tag hi mate. So this is how it works. The GUI is very simple. We can close it, and the Raspberry Pi still is attached, so we can just launch it again. You can write something. We can write again to the tag. We can send. If we press OK, it will be shown here. Tag successfully written. OK, and well, that is it. So yeah, that is it for the code explanation video. I think I went quite fast this time. It's not a 20-hour video. You can read, of course, more on the GitHub repository. Everything is over there, so that is not a problem. And then as a bonus, I will fix the NeoVim error I'm getting. One thing I want to talk, which I did not mention about Python being really terrible, is the fact that, well, we can stop socket. Is the fact that the highlighting and everything is just absolutely annoying to set up. It rarely works. I even started doing a custom NeoVim config, and yeah, I'm just doing everything manually. And I use RAF for linting and formatting, and piad for type tracking. I have like this really nice thing. So they tell you in Python that this bullshit that types are dynamic, and well, you can assign types dynamically, but if I press F5 to show inlay hints, we get types assigned. So after serial read, we get bytes as an output. Also, serial is a data type, so it is assigned as a data type. Then you also can return none, which is like void. Content is a string, the coding bytes yields a string, byte array is a byte array. So it's not that, it's not this dynamic typing bullshit they tell you. It's actually semi-statically typed, and well, you can assign dynamic stuff. So if I go here now and define a list, so age equal, so this is any because it's equal to anything. Now it's a list of anything, and then I start typing here numbers, so it's a list of integers. Then I do age dot append, and I can append a string. That's true. And then if I do age equal, well, I don't know how to get the inline hint for age now, but type age. I think this would print the type of age, and you would get a list of int or string. So if I start with string, what? Doesn't work. And so the LSP is broken. But before a moment ago, I've checked it like in the morning, and it was correctly telling it is a list of integers and strings. But well, now it's broken. So anyway, Python is really annoying, and they tell you a lot of propaganda about programming languages. If you want actually a good scripting language, I would say Lua. I started liking it fairly recently, and it's quite easy to structure your code, unlike in Python. And well, it is quite nice to program in this language. I quite like it. And yeah, that would be it for this video. And